My name's Gabe.
Hello and welcome to Pre-Calculus, Chapter 12, Section 2, Day number 2. In the last video, in day number 1, we saw some algebraic techniques to simplify limits. We had the dividing out technique where we would factor and cancel. We could multiply by a conjugate. We could combine fractions. But when we encounter a limit like this, those techniques aren't going to work. We've got x approaches 0, 1 plus x to the power 1 over x. If we try direct substitution, we're going to get 1 plus 0, that's 1, to the exponent 1 over x, or 1 divided by 0. So here's where we run into trouble. We don't know what's going on with this limit, and we can't factor and cancel, though we can't multiply by a conjugate. So we're going to go back to some of the stuff we saw in 12-1, and we're going to do an approximation. One way to do that is a numerical approximation. So our approach number is 0. Let me go this way. So we can't plug in 0, we get undefined. Let's go a little to the left of 0, negative 0.0001, and we can check on the other side, positive 0.0001. And if I plug that into my calculator, and I'll take it to about 4 decimal places, the negative decimal has an output of about 2.7184. And then if I plug in the positive 0.0001, I get a different 2.7181. So what looks like happens here is this number's a little higher, the 8.4. This number's a little lower, the 8.1. So it looks like our function is coming downhill as we go left to right. We've got a hole in our graph here at 0. But what we can do is kind of take the average in between these two numbers. What's right in between the 1 and the 4? Well, we could say this is approximately 2.718. We could do 2 or 2.5 or even a 3 there would be fine. Remember, we're just doing an approximation here. The limit does exist. You know, it's going to be close. It's going to be in between these two outputs. So there's our numerical solution. We can do that with a table of values. We could also, if we get our hands on the graph of this, if I was to put this in my graphing calculator, at 0, our graph does have a hole in it, and we already figured out it's sort of coming in for a landing like this. And the limit we found numerically, right here, that's going to be approximately the 2.7183. So we could do it numerically with a table. We could look at a graph on a graphing calculator. All right, and here in example 5, we've got something kind of odd, sine of x over x. The limit as x approaches 0. If we try direct substitution, we're going to have sine of 0 over 0, and the sine of 0 is 0. So we have encountered the indeterminate form. Now here, after example 5, it does say approximate the limit graphically. So we could put sine x over x into our y editor on our TID9s. And if we graph it, we're going to see something that's kind of a bell curve shape. Here we will cross the x-axis, so it's not really a bell curve. But we can see here at 0, here 0 would be the origin. If we go up, our graph is there, so our graph probably has a hole in it. And we want to estimate the height of that hole. Well, this line is labeled as 2, and this looks like about halfway down. So my estimate would be that limit is going to be 1. If we did this on a TID9, you could activate the trace feature, and you'll get a little blinking cursor, and we could move that cursor along this curve, and we could sort of estimate the top of that limit. And then we would see down in the corner our x-coordinate would be pretty close to 0, and our y-coordinate would be pretty close to positive 1. So there, if we do it the way the book says, find that limit graphically, that's how we could pull that one off. We could also do this one by a table of values. So if 0 is our naughty number, we could plug in a negative. Oop, I'm on the wrong page in my notes. Let's plug in a negative 0.01 and a positive 0.01. Now my negative 0.01 output is a 0.99998, so 0.49 and an 8. And then our positive 0.01 input would give us the exact same value. So in the other example, one value we were coming in for a landing. As we went left to right, we might be going up and our y value is getting bigger. Here the y values are exactly the same. So if we go out a little farther, if I was to do a negative 0.02, my y value would be 0.99993. So it looks like as we're coming here from the left, we're increasing. We went from 0.93 on the end to a 9.8, so we're going uphill. If I come to the other side here and put in a positive 0.02, that's going to give me 0.99993. Same on the other side. So here we went from this 9.8 to a 9.3. So graphically, what looks like it's happening is we're coming up to a peak, and then after the peak, we're coming back down. So we could visualize sort of rounding this up or rounding this up. Both of these numbers would round up to a positive 1. And remember, the positive 1 is what we saw when we looked at the graphical estimation. Again, the peak of our hill here looked to be at a y value of positive 1. All right, now here's a couple to try. This would be difficult at home without, a graphing calculator that you could plug these into. So if we try direct sub, we'll get e to the 0 minus 1. E to the 0 is 1. Anything to the 0 is 1. So our numerator is 1 minus 1. Our denominator, we directly sub in the 0. So we do get the dreaded 0 over 0. In this case, again, I would just do a quick table. Numbers really close to 0, negative 0.0001, positive 0.0001. And if I plug in that negative decimal, my output is 0.99995. On the other side of 0, I get a positive 1.0001. So it looks like our graph is increasing. This number's a little bit under 1. This number's a little bit over 1. So it looks like our graph is going uphill here. And at 0, we have a hole. But what would be the average in between these two y values, if we added them together and divided by 2, it looks like a 1 is going to come out. So that looks like our limit is equal to a positive 1. Ooh, there we go. Another one, 1 minus cos x over x. Our limit is approaching 0. So if I plug in 0, I'm going to get 1 minus the cos of 0. The cosine of 0 is 1. And our denominator, we would just directly plug in that 0. So once again, indeterminate form, 0 divided by 0. So let's do a little table of values. Once again, our approach is to 0, so we can conveniently use negative 0.0001. Our output there would be negative 0.4 zeros and a 5. And let's try the other side of 0, positive 0.0001. Our y value there would be a positive 0.00005. So here our graph is going uphill. We're negative, and then we cross to positive. So it looks like our output for 0 should be something in between negative and positive. And what's right in between negative and positive? 0. So this limit looks like it's going to turn out to be a 0. Okay. Now before we start this slide here, I want to do a quick refresher. Remember, there are 3 times a limit fails to exist. Let's say we're approaching this number c, and as we come in from the left, we're up here. And if we come in from the right, we're down here. So we would say that this limit does not exist. We're not approaching the same hole. We've got an obvious big jump in our graph, so that limit will not exist. We can refine our idea of a limit, and we can approach just this limit from one side, a limit from the left, and we'll find the height of this hole. And we can approach the other hole from the right and find the height of this hole. The overall limit will not exist, but the one-sided limits will. So that's our last little topic here in this video, a one-sided limit. Now you're going to see a little change in the notation. Like, let's say we have our limit as x is approaching 0. If I want to approach 0 from the right, I'm going to put a little plus up there. Because on the number line, where 0 is, the positive numbers are to the right of 0. The negative numbers are to the left. So if we're going to approach only from the right, we'll have that up there. That's a right-hand approach. And if our limit as x approaches 0, if we put a little superscript of a negative, that means we're coming in from the left side. So these are different limits, the limit from the right, the limit from the left. If we combine them overall, that would be our limit as x approaches 0. You know, sometimes this will be does not exist due to approaching two different numbers. Here's where we would find those two different numbers that we're approaching. So, in section 12.1, you saw the limit can fail to exist, blah, 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 blah. This type of behavior can be described more concisely with a one-sided limit. So here we can see real small, x approaches c from the left, and x approaches c from the right. So let me move this up here. Example 6. Find the limit of f of x as x approaches 0 from the left and the right side. So we've got our absolute of 2x divided by x. We've seen a graph similar to this before. Here is our graph of this. Again, to the right of the y-axis, we would be plugging in positive x values. So our numerator are going to be positive numbers. The bars will keep them positive. Our denominators will be positive. So this we're going to divide 2x divided by x. The x's would cancel. And our value left would be positive 2. So here, as we're approaching from this side, we're approaching positive 2. So let's write that out in our new notation. The limit, as x approaches 0 from the right, of the absolute of 2x over x, that limit is equal to positive 2. And now I'm going to switch to red ink, come down here. We're going to approach 0 from the left side. The limit, as x approaches 0 from the left, of the absolute of 2x over x, well, that's going to equal negative 2, because we're down here approaching this hole. Now, let me get a little more space here. So, the left-hand limit exists. It's a negative 2. The right-hand limit exists. It's a positive 2. So now we can combine these and say overall, the limit as x approaches 0 of the absolute of 2x over x, that limit does not exist. And remember, in my class, when you say a limit doesn't exist, I want to know which one of the three reasons why it doesn't exist. So here we could make a note, this limit doesn't exist due to approaching two different numbers. Approach two different numbers from the left and the right. But here we can be a little more concise. As we come in from the right, we're approaching 2. As we come in from the left, we're approaching negative 2. So the overall limit fails to exist. Whoa, nice little glitch there. The overall limit fails to exist. Ooh, why do I have this on here twice? Okay, just a little rerun. Same answer. The limit does not exist. And I got it there again. Okay. So, existence of a limit if function f. If f is a function and c and l are just real numbers, then the limit as x approaches c of f of x is equal to L if and only if both the left and the right limits exist and they are both equal to that number L. They have to be converging on the same value. Now, in example 7, they talk about these one-sided limits in the context of a piecewise function. So it says, find the limit as x approaches 1. Our function, if x is less than 1, we're going to plug that x value in the top piece of the function. If our x value is greater than 1, we plug that x value in the bottom piece of the function. Notice there is no or equal to here. So if we get a 1, we have no place to plug it in. But remember, this limits are about the approach as we get close. So if I want to analyze this one, I'm going to plug 1 into the top piece of the function, and I'm going to plug 1 into the bottom piece of the function. Even though there is no or equal to, remember, it's all about the approach. So I'm going to write the limit as x approaches 1 from the left side, and I'm just going to write f of x. I'm not going to copy the whole function. So from the left side, that would be numbers less than 1. So I'm going to directly plug the 1 right into the function. So that's going to equal 4 minus 1. 4 minus 1, last I checked, is 3. Okay, I'm going to switch to blue ink. And now we're going to do the limit as x approaches 1 from the right side, from numbers bigger than 1. So that means we're down here, where x values are greater than 1. I'm going to just plug a 1 directly in for both of these x's. So this limit, as we approach from the right, will be 4 times 1 minus 1 squared. 4 times 1 is 4. 1 squared is 1. Subtract 4 minus 1 is 3. So it looks like the left-hand limit is 3. The right-hand limit is also 3. So we could write the overall limit, the limit as x approaches 1 of f of x, is also equal to 3. You know, remember, if we're approaching two different numbers, the limit fails to exist. Here we're approaching the same number, 3. So the limit does exist, and it's equal to 3. Now, what was going on here graphically? If we were to graph the piecewise, it would look like this. To the left of 1, we have a negative sloped line, 4 minus x. Here's our negatively sloped line. I'll hit it in red ink. Now, as we approach x is 1, we're going to now jump to the other function. The other function, 4x minus x squared, is a downward opening parabola. Notice that the red negatively sloped line left off right where the blue upward or upside down parabola starts. So they both were approaching this same hole. That hole is a height of 3 on the y-axis. That is our limit. Excellent. I think we just got a couple of checkpoints for you to try. So again, try the video, or pause the video here and try these out, and then fire it back up and see if you got it right. Okay, I'm going to graph this real quick first. X minus 3 is in bars. If I set what's in the bars equal to 0, I would get x is 3. So that is where we're going to jump from one part of this to the other. Okay, if I plug in a number bigger than 3 like 4, I would have the absolute of 4 minus 3, that's 1. Over the denominator 4 minus 3, which is also 1. 1 divided by 1 is 1. So here we're going to be approaching positive, or we're going to be on 1 approaching 3 from the right. So let me write this in red ink. The limit as x gets close to 3 from above, from the right, of f of x is equal to positive 1. Now let's plug in a number less than 3, like 2. So in the numerator, I would have 2 minus 3 in bars. 2 minus 3 is negative 1. The bars would make that numerator a positive 1. And then I would put the 2 in the denominator. 2 minus 3 is negative 1. So these would divide out to a negative 1. So I could write my limit as x approaches 3 from the left side, from values below, of f of x is negative 1. So now I got my left and my right limits. I can look at them together and say this limit as x approaches 3 of f of x does not exist. D, N, E. And the reason would be approaching two different numbers from the left and the right. We got a gap in our graph. Oh, if I graphed it up here, we'd be coming down here. I should use blue ink. We would be approaching here at negative 1 as we approach 3. So there's our gap in the graph. That's the smoking gun. The limit failed to exist. All right, now a piecewise. Mind your negatives and your order of operations. So it says here we're approaching negative 1. So I'm going to use red ink for the top part. we're going to find our limit as x approaches -1 from the left from numbers underneath. Now I'm going to plug a -1 into this top piece. Now be extra cautious with this negative. We've got the negative in the function, and then our x that we're going to square is a -1, and then we're going to have -3. The x is gone. I'll replace that with a -1. So let's see here. -1 squared is 1. This will maintain it is a -1. And then this -1 and -3 will multiply to a +3. -1 plus 3 is equal to +2. So I'm just going to erase here, going to make this equal to +2. The limit from the left is +2. So now for the other side, for numbers greater than -1, I'm going to use this bottom piece. But again, we're just going to directly sub in that -1. So as we approach -1 from the plus side of our function f of x, that's just going to be x plus 3, or -1 plus 3. -1 plus 3 is +2. So our limit from the left is 2. Our limit from the right is 2. So we can say the overall limit, the limit as we approach -1 of our function f of x, is also equal to +2. Where the top function left off, the bottom function picked right up. So that's why we have our same output value, +2. Okay, and that's a good place to stop the video. We will do some practice problems tomorrow in class, and then you'll have some time for the WebAssign, and I will see you then.